Beyond MapReduce. Although MapReduce became very popular and received a lot of hype in the late 2000s, it is just one among many possible programming models for distributed systems. Depending on the volume of data, the structure of the data, and the type of processing being done with it, other tools may be more appropriate for expressing a computation. We nevertheless spent a lot of time in this chapter discussing MapReduce because it is a useful learning tool, as it is a fairly clear and simple abstraction on top of a distributed file system. That is, simple in the sense of being able to understand what it is doing, not in the sense of being easy to use. Quite the opposite. Implementing a complex processing job using the raw MapReduce APIs is actually quite hard and laborious. For instance, you would need to implement any join algorithms from scratch. In response to the difficulty of using MapReduce directly, various higher-level programming models Pig, Hive, Cascading, Crunch were created as abstractions on top of MapReduce. If you understand how MapReduce works, they are fairly easy to learn, and their higher-level constructs make many common batch processing tasks significantly easier to implement. However, there are also problems with the MapReduce execution model itself, which are not fixed by adding another level of abstraction and which manifest themselves as poor performance for some kinds of processing. On the one hand, MapReduce is very robust. You can use it to process almost arbitrarily large quantities of data on an unreliable multi-tenant system with frequent task terminations, and it will still get the job done, albeit slowly. On the other hand, other tools are sometimes orders of magnitude faster for some kinds of processing. In the rest of this chapter, we will look at some of those alternatives for batch processing. In Chapter 11 we will move to stream processing, which can be regarded as another way of speeding up batch processing. Materialization of intermediate state. As discussed previously, every MapReduce job is independent from every other job. The main contact points of a job with the rest of the world are its input and output directories on the distributed file system. If you want the output of one job to become the input to a second job, you need to configure the second job's input directory to be the same as the first job's output directory, and an external workflow scheduler must start the second job only once the first job has completed. This setup is reasonable if the output from the first job is a dataset that you want to publish widely within your organization. In that case, you need to be able to refer to it by name and reuse it as input to several different jobs, including jobs developed by other teams. Publishing data to a well-known location in the distributed file system allows loose coupling, so that jobs don't need to know who is producing their input or consuming their output. See separation of logic and wiring on page 396. However, in many cases, you know that the output of one job is only ever used as input to one other job, which is maintained by the same team. In this case, the files on the distributed file system are simply intermediate state, a means of passing data from one job to the next. In the complex workflows used to build recommendation systems consisting of 50 or 100 MapReduce jobs, there is a lot of such intermediate state. The process of writing out this intermediate state to files is called materialization. We came across the term previously in the context of materialized views, in aggregation, data cubes and materialized views on page 101. It means to eagerly compute the result of some operation and write it out, rather than computing it on demand when requested. By contrast, the log analysis example at the beginning of the chapter used Unix pipes to connect the output of one command with the input of another. Pipes do not fully materialize the intermediate state, but instead stream the output to the input incrementally, using only a small in-memory buffer. MapReduce's approach of fully materializing intermediate state has downsides compared to Unix pipes. A MapReduce job can only start when all tasks in the preceding jobs that generate its inputs have completed, whereas processes connected by a Unix pipe are started at the same time, with output being consumed as soon as it is produced. Few or varying load on different machines means that a job often has a few straggler tasks that take much longer to complete than the others. Having to wait until all of the preceding job's tasks have completed slows down the execution of the workflow as a whole. Mappers are often redundant. They just read back the same file that was just written by a reducer and prepare it for the next stage of partitioning and sorting. In many cases, the mapper code could be part of the previous reducer. If the reducer output was partitioned and sorted in the same way as mapper output, then reducers could be chained together directly, without interleaving with mapper stages. Storing intermediate state in a distributed file system means those files are replicated across several nodes, which is often overkill for such temporary data. data flow engines. In order to fix these problems with MapReduce, several new execution engines for distributed batch computations were developed, the most well-known of which are Spark, Tez, and Flink. There are various differences in the way they are designed, but they have one thing in common. They handle an entire workflow as one job, rather than breaking it up into independent subjobs, since they explicitly model the flow of data through several processing stages. These systems are known as data flow engines. Like MapReduce, they work by repeatedly calling a user-defined function to process one record at a time on a single thread. They parallelize work by partitioning inputs, and they copy the output of one function over the network to become the input to another function. Unlike in MapReduce, these functions need not take the strict roles of alternating map and reduce, but instead can be assembled in more flexible ways. We call these functions operators, and the data flow engine provides several different options for connecting one operator's output to another's input. One option is to repartition and sort records by key, like in the shuffle stage of MapReduce. See distributed execution of MapReduce on page 400. This feature enables sort, merge, joins, and grouping in the same way as in MapReduce. Another possibility is to take several inputs and to partition them in the same way, but skip the sorting. This saves effort on partitioned hash joins, where the partitioning of records is important, but the order is irrelevant because building the hash table randomizes the order anyway. For broadcast hash joins, the same output from one operator can be sent to all partitions of the join operator. This style of processing engine is based on research systems like Dryad and Nefel, and it offers several advantages compared to the MapReduce model. Expensive work such as sorting need only be performed in places where it is actually required, rather than always happening by default between every map and reduce stage. There are no unnecessary map tasks, since the work done by a mapper can often be incorporated into the preceding reduce operator because a mapper does not change the partitioning of a dataset. Because all joins and data dependencies in a workflow are explicitly declared, the scheduler has an overview of what data is required where, so it can make locality optimizations. For example, it can try to place the task that consumes some data on the same machine as the task that produces it, so that the data can be exchanged through a shared memory buffer rather than having to copy it over the network. It is usually sufficient for intermediate state between operators to be kept in memory or written to local disk, which requires less I/O than writing it to HDFS, where it must be replicated to several machines and written to disk on each replica. MapReduce already uses this optimization for mapper output, but data flow engines generalize the idea to all intermediate state. Operators can start executing as soon as their input is ready. There is no need to wait for the entire preceding stage to finish before the next one starts. Existing Java Virtual Machine JVM processes can be reused to run new operators, reducing startup overheads compared to MapReduce, which launches a new JVM for each task. You can use dataflow engines to implement the same computations as MapReduce workflows, and they usually execute significantly faster due to the optimizations described here. Since operators are a generalization of map and reduce, the same processing code can run on either execution engine. Workflows implemented in Pig, Hive, or Cascading can be switched from MapReduce to Tez or Spark with a simple configuration change, without modifying code. Tez is a fairly thin library that relies on the Yarn Shuffle service for the actual copying of data between nodes, whereas Spark and Flink are big frameworks that include their own network communication layer, scheduler, and user-facing APIs. We will discuss those high-level APIs shortly. An advantage of fully materializing intermediate state to a distributed file system is that it is durable, which makes fault tolerance fairly easy in MapReduce. If a task fails, it can just be restarted on another machine and read the same input again from the file system. Spark, Flink, and Tez avoid writing intermediate state to HDFS, so they take a different approach to tolerating faults. If a machine fails and the intermediate state on that machine is lost, it is recomputed from other data that is still available, a prior intermediary stage if possible, or otherwise the original input data, which is normally on HDFS. To enable this recomputation, the framework must keep track of how a given piece of data was computed, which input partitions it used, and which operators were applied to it. Spark uses the Resilient Distributed Dataset RDD abstraction for tracking the ancestry of data, while Flink checkpoints operator state, allowing it to resume running an operator that ran into a fault during its execution. When recomputing data, it is important to know whether the computation is deterministic, that is, given the same input data, Do the operators always produce the same output? This question matters if some of the lost data has already been sent to downstream operators. If the operator is restarted and the recomputed data is not the same as the original lost data, it becomes very hard for downstream operators to resolve the contradictions between the old and new data. The solution in the case of non-deterministic operators is normally to kill the downstream operators as well, and run them again on the new data. In order to avoid such cascading faults, it is better to make operators deterministic. Note, however, that it is easy for non-deterministic behavior to accidentally creep in. For example, many programming languages do not guarantee any particular order when iterating over elements of a hash table. Many probabilistic and statistical algorithms explicitly rely on using random numbers, and any use of the system clock or external data sources is non-deterministic. Such causes of non-determinism need to be removed in order to reliably recover from faults, for example by generating pseudorandom numbers using a fixed seed. Recovering from faults by recomputing data is not always the right answer. If the intermediate data is much smaller than the source data, or if the computation is very CPU intensive, it is probably cheaper to materialize the intermediate data to files than to recompute it. Returning to the Unix analogy, we saw that MapReduce is like writing the output of each command to a temporary file, whereas dataflow engines look much more like Unix pipes. Flake especially is built around the idea of pipelined execution, that is, incrementally passing the output of an operator to other operators, and not waiting for the input to be complete before starting to process it. A sorting operation inevitably needs to consume its entire input before it can produce any output, because it's possible that the very last input record is the one with the lowest key and thus needs to be the very first output record. Any operator that requires sorting will thus need to accumulate state, at least temporarily. But many other parts of a workflow can be executed in a pipelined manner. When the job completes, its output needs to go somewhere durable so that users can find it and use it. Most likely, it is written to the distributed file system again. Thus, when using a dataflow engine, materialized datasets on HDFS are still usually the inputs and the final outputs of a job. Like with MapReduce, the inputs are immutable and the output is completely replaced. The improvement over MapReduce is that you save yourself writing all the intermediate state to the file system as well.